Okay, well, I think in the interest of staying on schedule and sticking to our traditional 3:30 Wednesday afternoons in the spring semester, I'm going to officially kick things off. And first of all, welcome everyone to the final Water Center Spring Seminar of 2020. This is an interesting way to conclude what's been an interesting last 6 weeks or so. But thanks to technology like Zoom, we're able to still have these seminars. And I see that right now we have 47 people participating. I hope that everyone can both see the screen with Dr. Panday's PowerPoint and hear my voice. My name is Jesse Starita. I'm the Public Relations and Engagement Coordinator with the Nebraska Water Center here at the University of Nebraska-Lincoln. We're part of the Doherty Water for Food Global Institute. And this is the last seminar, but if you would like to access previous seminars, they're available on the Nebraska Water Center's YouTube channel. We've been posting them there within about a day or so of the seminar's completion. One quick housekeeping reminder, and then I'll introduce Dr. Panday. If you're joining the call and your microphone is not muted, I would encourage people to please mute their microphones. That'll just make for a smoother experience for everyone here who's joining the call. So thank you all for being here. Dr. Sorab Panday is a principal with GSI Environmental Incorporated. He has more than 28 years of experience in directing, managing, developing, troubleshooting, and reviewing flow and transport models for subsurface contamination evaluations and water resource management. He has worked on hydrologic and hydrogeologic modeling projects spanning a wide range of schedules and budgets of multiple spatial and temporal scales, complex geological settings, diverse climatic conditions, unique water contaminant management issues, and challenging numerical conditions. Sorab is a native of Mumbai, India, and he has developed several of the industry's state-of-the-art water resource modeling codes and is the lead author on ModFlow USG, an unstructured grid version of ModFlow released by the USGS. He was also awarded the M. King Hubbert Award by the National Groundwater Association in 2015 and was inducted into the National Academy of Engineering in 2017. No small feat. Finally, last year, Sorab joined the faculty at UNL. So he's part of our family now. He is a research professor in the Department of Biological Systems Engineering and the Nebraska Water Center, but he's joining us this afternoon, well, we'll call it quarantined in his office in the Washington, D.C. area. And if all goes well, I'm going to pass things off to him to talk about understanding your water resource with groundwater modeling. Sorab?
Hey, thank you, Jesse. Can you hear me? All right, very good. Well, I was born in Mumbai, but I'm a native of Herndon, Virginia. I've lived here, well, seems like all my life. And let me start with this. I'm just going to talk about, well, as the topic says, understanding your water resource with groundwater modeling. And if I can get the slides to change, there we go. So just what I'll cover is, first of all, what is groundwater modeling? And what we do is create computer simulations of groundwater flow to evaluate impacts of natural and man-made stresses, like pumping, for example, on water levels and flows. And then we say also water quality, because these are the issues of concern that we are trying to address with groundwater modeling. So then second point is we'll just talk about how can groundwater modeling help, what industries, where is it applied, and then we'll just talk about how to construct a groundwater model. and end off with perceptions of groundwater models. Are we doing a good job? And then where we are headed in the future. So with that, how do I see groundwater modeling? I've pretty much been a consultant all my career. And for us, in consulting, groundwater models are used to understand processes, manage resources, and solve problems. That is the big thing. We do modeling to solve problems. Things like how much groundwater is available, where are contaminants going, and when will they get there? How should we manage the resource? How do varying stresses and parameters interact with each other? How does that impact the aquifer? What is the impact of uncertainties? When you're in a groundwater model, there's a lot of unknown. So what is the impact of that on the results of what I'm trying to achieve? And then we always try to make better computer models where you don't use an elephant gun to kill a fly. You develop customized solutions so you are solving exactly the client's issues and not wasting time and budgets. And you explore the impact of uncertainties. Again, coming back to it, that there are a lot of unknowns. So maybe you want to pin those down better. Or maybe you want to analyze things in certain extreme cases so you can be more conservative in your management practices. Okay, and just a little background. Thank you, Jesse. You gave a good background. This is more of my career background. Where do I get all this from? Well, I've just done pretty much groundwater modeling from grad school onwards. In grad school, I was doing something more, research oriented, looking at NAPL and permafrost and heat interactions with soil water. In grad school, I taught one of the first mod flow courses in New York. That was my summer job, right? To get some money in summer. And Jacob Bear and Dr. C were teaching this course. But since I graduated, I've just been doing consulting with modeling. I've developed and applied finite element models, various processes, fractures, density dependent saltwater intrusion, multi-phase. I've done finite difference models, physically based surface water subsurface interactions, control volume codes. So I've gone through the whole gamut of numerical methods and essentially applying models to evaluate clients' needs. I've been involved in theses and committees of students for the last 30 years at UC Davis and University of Waterloo. I interact with the professional modeling community all the time for support and training because I've been developing all these codes. So people ask for support and training. So I see their issues and problems. So that's interesting. I interact with leading scientists from universities and the USGS. My ModFlow USG code was pretty much a collaboration with the USGS. And I interact with colleagues at conferences, seminars, and workshops. So as you can see, pretty much my whole career life has been doing modeling. Okay, I better find it interesting, right? And I do, so that's good. Okay, how can modeling help? Where does it help? It can help in understanding and managing the resource as well as the consequences across industries. And for instance, I have some industries over here, Department of Energy, they are looking at waste disposal, sequestration. They have, radioactive contaminants they want to sequester in the ground, carbon, nitrogen, phosphorus sequestration. Different industries do groundwater modeling or apply groundwater modeling. Oil and gas, they need to see how they need water in the upstream side and in the downstream side. Downstream side in the sense of, okay, your contaminants, what do you do with the waste, with the brines that come out? Chemical industries, the contamination issues which we address through modeling. Mining, again, upstream and downstream. In mining, they need to dewater the mine. So they are using groundwater modeling to estimate how to dewater the mines. On the downstream side, you have tailings. So how do you handle the tailings? Agricultural, yes, Nebraska is an agricultural state. So pretty much we know our water issues here. You can see beautiful Lincoln behind in my background, right? So anyway, Very pretty place. I wish I was there. 75 degrees are here today. Eh? But anyway, agricultural, again, you'll have issues with upstream, with irrigation, as well as then the downstream issues with nitrogen, phosphorus, and things like that, with surface water interactions. Then there are nonprofits who hire groundwater modelers. Landfills, you are looking at how landfill leachates hit the groundwater. Water purveyors and districts, water districts, they want to understand how to manage their water resources. Attorneys, there are water disputes. So attorneys hire groundwater modelers, if you believe it or not, to try and understand how to resolve these issues. Regulatory agencies, water control boards, environmental quality boards. Insurance agencies, there are again environmental damage claims. So they want to look at those. So you'll use modeling to try and evaluate that. Department of Defense, they have their issues and many more. So you can see there's a wide gambit of industries where groundwater modeling becomes important. What are the issues? Essentially, there's freshwater supply in a lot of these industries. There are water quality issues in a lot of these industries. Things like saltwater intrusion in coastal aquifers. And yeah, nitrates in agricultural regions. And others, there are other unique questions that can be answered, issues that can be resolved with groundwater modeling, and interesting things like heat and geothermal. So you can look at heat in the groundwater as a resource, and you're using that to heat or cool buildings. Land subsidence are issues, permafrost issues. So these are, different issues like dam stability. So with more water in your pores, you are losing the effective stresses. So all these things use groundwater modeling to evaluate conditions and try and address issues and manage resources. So let's move on. As we see, there are lots of applications of groundwater modeling, and I thought let's spend some time on looking on what do we do? What are we doing sitting in our offices? And as an example, I have this lower Rio Grande Valley basin that we worked on a couple of years ago. And I thought I'll bring that up to show this is what we do to construct a groundwater model. So the first thing is, why are we doing this modeling? Well, in this case, what we wanted to know was how does pumping impact surface water flows and levels? How does the salinity of the groundwater change due to pumping? So this is the lower Rio Grande Valley basin. Pretty much the groundwater here is brackish. So you pretty much need to have reverse osmosis to even use that water. They have a few RO systems there. They were planning on building, I believe, 17 or so more RO systems. So this was to help with design of those systems and evaluation of the impacts on the resources. So salinity was a big thing, and you needed to know what the salinity was of the water coming into those reverse osmosis systems, because that helps with the design of those systems. They wanted to look at how your ground is subsiding because of groundwater pumping. And there were uncertainties, as there always are in our subsurface. And here, one of the big things was faulting and what was the impact of faulting. So once we understand what our objectives are, then we can design the model accordingly. So first thing is, after the objectives, is try and create a geologic conceptual model. What does the piping as such, what does your reservoir, what does your aquifer system in the subsurface look like? So you start your geologic conceptual model, you start looking at geologic formations, you start looking at your hydrogeologic units, so you can separate them into hydrogeologic units. Maybe you need to simulate each geologic formation separately. You create a box model as such to try and understand what the subsurface looks like. You could look at them in cross sections to east-west, north-south, again, to understand if there are pinch outs, if there are outcrops of these aquifer units. And finally, you look at things like fractures and faulting, which may affect flow. Okay, so what you are building, first thing is your subsurface geology in a computer environment. Next thing is you create your hydrogeologic conceptual model. So what is the water going in there? How is the water coming out? So those are the issues you look at next. So you're building your hydrogeologic conceptual model. What is your annual average precipitation? Your input. How much is your evapotranspiration? What is leaving the model domain and where? Your stream flows and base flows. So here, this over here, I hope y'all can see my cursor moving here. Well, maybe I can throw in a laser pointer. That is the Lower Rio Grande. So you can see flows at the different locations. You can look at try and understand the base flow from flow differences. You have diversions from the river, and those diversions then are used to irrigate lands around there. So you need to pull out the water at the diversions and irrigate the lands there. And then you have pumping. So all this is the information that you want to put into your groundwater model. So your groundwater model can then replicate the system that you are trying to mimic as such in your model. And what is the system you are trying to mimic in your model? Essentially, they are the water levels, which you know through measurements of water levels at various observation wells. So you know how they fluctuate, for instance. You may have created maps of your water tables or potentiometric surface, as it is called, in the various aquifer units. And you want to say, okay, in general, that behavior, can I replicate that? Because these maps indicate, potentiometric maps kind of indicate the flow behavior, right? Flow will be from a higher potential to a lower potential. And if there's no density effects, if there's no anisotropy, it pretty much will be perpendicular to the potentiometric contours. So now we are building up our model in a conceptual sense. This is just another aquifer. Again, water levels in that aquifer, water levels in the lower aquifer, and again, the potentiometric surfaces in various years, how the water levels fluctuate through time. So once we have our conceptual model ready, you can start building the numerical model. And essentially, again, what we are doing is, remember this, a conceptual model is you are putting in the significant driving factors into the model. You are not worried about things that are extraneous to your objectives, right? I mean, there may be so many other things going on in the subsurface, heat or something. We are not looking at that here. So again, it's the significant processes, significant governing processes are what you are trying to represent in your conceptual model. So it's a simplification of that reality focused on your objectives. Now, when you take your conceptual model, you're translating it to a numerical model. There is one more level of approximation going on in that. And first is to create a numerical model, you create a grid, a finite difference, finite volume, finite element grid. This is a finite volume grid. You can create finer resolution around the river, so you can capture the interactions better. But each grid block then is parametrized. You create this grid. It can be deformed in the vertical to represent exactly the geology, the way you'd conceptualized it, including the pinch outs. You can throw in the faults into your model. There are all these packages in numerical models which allow you to do that. Then this model we parameterized by estimated sand fraction. So for each of the aquifer units we had, or I should say the hydrostratigraphic units, we had sand fraction. So we decided, let's make use of this information and parameterize it that way. So you had a sand and a non-sand. So a high K material and a lower K hydraulic conductivity material. And then the conductivity value itself becomes calibration of the model. What is calibration? Is you're trying to match the observed behavior. But so what we have done now here is created a discrete representation of the geology. Now we need to throw in the hydrogeology, throw that water in there. There's precipitation, all the stuff we looked at before, evapotranspiration, pumping, the diversions from the rivers, the irrigation, where you return that flow back. So there are packages available to develop all these in the numerical model, but now these are again done discretely. You don't have continuous data for one, but you take and you can do seasons or things like that. So you discretize them into seasons for time, and then you input that accordingly. You have lateral boundaries. Flow may be coming in and out of the lateral extent of your model boundary. So you need to have that. If there are geological constraints to flow, there'll be no flow boundaries. Or you can say, we know the water level here in the sea, it's 0. So let's use a 0 water level condition as the boundary here, and water can flow into the sea under those conditions. So those are the things you put into your numerical model. You've created one more level of simplification. And then you go and calibrate that numerical model. So you change those parameters, you change those hydraulic conductivities, which are really unknown, right? Because we don't know those values, but you change them such that it matches the observed behavior. And we look at various statistical metrics to say, yeah, my model is doing what I want it to do. For instance, you look at the regression between simulated and observed water levels and say, yeah, my simulated and observed water levels match. You look at the spatial bias in results. Are there like only red dots in one place where the model simulates low, and blue dots in another place where the model simulates high? So you can look at the distribution of errors that way, see where the errors are large, and actually our errors are large here in the location of these fractures, which do create some issues in cross-formational flow. They create, because these are displacement fractures actually, they create issues with also blocking flow from one side to the other. So these are some things we needed to evaluate. But in general, you compare water levels and trends. You're not gonna match every fluctuation, but generally where you see water levels fluctuate a lot, the simulation does something similar. Where water levels are kind of flat, the simulations are flat. So you know that your model is responding to changes in stresses, say because of pumping, because of recharge changes, seasons, climatic, whatever it may be. Over the years, there could be droughts, so there could be long-term declines. There could be a lot of pumping increases that could cause long-term declines. So now what you have done is you have tried to match what was out in the field, the significant parameters to your objectives in the model. You've matched things like the potentiometric surface contours. So you can see, overlay the simulated with the observed and say, yeah, I think I'm doing a good job. Once you have a calibrated model, you look at things like water budgets. Is the total water budget reasonable? Is the flows in the Rio Grande, are they reasonable? The groundwater budget, are they reasonable? These things you don't know in advance. You can estimate conceptually that, yeah, we know how much the pumping is there, but you don't know how much the evapotranspiration is. So those things round off your water budget, but they need to make sense. And that's something you see. And groundwater interaction flux, that is something you can estimate from your, as base flow from your stream gauges. If you don't have any diversions between stream gauges, or you can remove the diversion amounts and still kind of estimate what your base flows would be and try and see if you've matched those, So you are estimating things like your water levels, which are dependent on recharge and pumping. You're estimating things like your groundwater interaction flux, which depend on recharge and pumping. So your model is calibrated to those impacts. So now it might be good to look at future impacts, to We are not done yet. We need to look at what's called sensitivity analyses. In groundwater modeling, because these parameters are not that certain, we do these sensitivity analysis to see what is the impact. What if I change, what if my recharge was a little lower? How would that impact my model? How would that impact my errors? So we are actually looking at how these things impact errors. Impact of parameter uncertainty. If my K values, hydraulic conductivity values were different, how would that impact my errors? Then look at impacts along the barriers. So change the resistance of the barrier. How does that impact flows? Will that help me calibrate my model better? Am I understanding my system better because of it? And in different aquifer units, you may get different impacts, and so you try and understand those. Are there water levels nearby which I can test for these impacts? If these are critical locations, these are water supply locations, then you want to evaluate that further. If these are extraneous, it's part of your model, yes. Maybe, again, it's objective or driven, so every bit of your model need not be right. You focus on what your objectives are, you focus on what your client needs, and you don't try and massage other parts of the model. It's a waste of time and effort. So you try to understand things and you try to give them answers. And of course, in this one, there were chlorides. So we had to go through all that again to assimilate chloride data. So we are developing a chloride conceptual model, create distributions in the various aquifer units, evaluate if it is possible to calibrate those transport information. Usually with chlorides, it's not. But if you had, say, if you were looking at contaminants or something, you can see plumes and you can say, ah, yes, it started in the 50s. There's a 50-year history and it's moved this big. So can you generally match that with your model? Again, you have to develop source terms and you can do that conceptually. But a lot of times you start with a chloride distribution, which is what we did here. We had to estimate porosities, dispersion. For chlorides, there's no decay or adsorption, but we started with that distribution, initial distribution, and then we ran simulations with that to see how that would impact our concentrations due to pumping. And now we can look at the predictive simulations for this. These are predictive simulations. How do concentrations in these aquifers change due to pumping? So we can look at the absolute concentration values. We can look at change from the previous due to pumping. We can look at water levels and drawdowns, because that is also of interest. The larger the drawdowns, the more energy is required to pull that water out. You can look at how chlorides change through time at the different reverse osmosis plant locations to see what sort of filter capacities you may need, how often you may need to change those, things like that. We also looked at stream flow reductions at critical sections of the lower Rio Grande River. I'm not showing a picture here. We did not analyze subsidence here because it was not likely in this setting. So yes, it was one of the objectives. We looked at it. The pumping wasn't large enough. There wasn't much data beyond that, it's not likely. So that's where that ended. So you see how you take a model from beginning to end to answering your client's objectives. So now they can use that in their management efforts for developing the additional RO's capacities or whatever they need. Now, I just want to go into something. Are we doing a good job with groundwater models? I want to end off with this. Historically, yes, there are successes in management of water resources, because you calibrate your model very oftentimes to exactly the conditions in the aquifer, and yeah, it may be recharge, maybe extra, pumping may be less, but still the net volumetric budgets are being conserved. And since you're calibrating your model to that, we are doing a fairly good job with that. In adjudicated water rights, water banking evaluations, we are doing a very good job, I think. Why? Even if your model may have errors, what the models do is bring people together in an acceptable framework to talk to each other. So people say, I'm banking X amount of water and someone else is banking Y amount of water. And it's all done in the model. And the model says, yes, this is what the impact would be to your system. And you can bank that, you cannot. It's going to cause some issues if you bank all that water, or it's going to create issues if you take all the water out that you bank. So you see, all these things might be there. The model helps bring people together. And if the model is, when it's updated, people say, there's like 5,000 acre feet is missing, the model was wrong. So then everyone goes from their banks and say, okay, we'll evenly distribute out this 5,000 acre feet and come back to where we are. So you see, the model helps people get together, helps people manage their systems. And when those errors are there, frequent updates help adjust those errors, and people absorb that error in their water banking. So it's done a good job there also. Less so for solute transport because of local heterogeneities. We do these point measurements and we try to figure out where solutes are going, and we've had hard time with that. Maybe we need to look at other aspects in solute transport, and then also less so for karst systems. And again, with solute transport, karst systems, short circuit your transport pathways, when if it was a porous medium system, you don't see that. So we are not too successful with these. In karst systems, people use groundwater modeling in a conceptual method. Can we fit the data by this concept or that concept? So they play with concepts to try and understand it. Now, I do want to compare with weather prediction modeling and history. Why? Because they were kind of in the same boat as, where people were not very happy with their models, and they have improved in the past 20 years. And what have they done right? They have a lot more data. They continually update their models, and they evaluate uncertainties. This bottom right slide, for instance, picture, for instance, shows this multi-model approach that they use. You don't have to go into very complex uncertainties. You look at a few multiple models with different conceptualizations, which are still possible, plausible, and you look at those results. So yeah, that bullet under that, which I look at, is level of effort, cost versus benefit perspective. And I look at that again from for the weather prediction people, because people are pushing the modeling industry to say, do Monte Carlo analysis, do 20,000 simulations to figure out your uncertainty. And well, objectives and schedules be damned, I guess, But you look back at what these weather people are doing. They have to make decisions which are within days or weeks. Our decisions are months and years. They are making decisions which are critical in the top values of evacuating New Orleans or not, and this is human lives and millions of dollars, one way or the other. So they are making decisions this way with their level of effort. Yes, there is a lot of data they have. I understand we need to get more, but again, the perspective that you do is, for the risk that we are looking at, how much money should we be spending in doing modeling? Let's not become a self-absorbed institution of modelers. Modeling is a means and not an end. So finally, the whole thing comes down to communication of modeling efforts and uncertainty. And again, it comes back to, how are we talking with people? I think that is another thing, that whether people are doing better nowadays than us. We are making even more fancy graphics, so people are looking at our models even more truthfully than as models. And I think we need to communicate things better. People, when there's uncertainty, people communicate uncertainty with complex charts and things, and it can go way over your head. Maybe something simpler like a spaghetti plot, or maybe error bars might be easier to communicate. So again, I think we have an issue of needing to do a better job in communication. Industry trends and needs. How are we moving? What are the drivers right now? Is community modeling, really, with input from regulators, stakeholder consultants, everyone, and people want to see conservative modeling a lot of times, because it is for management purposes. So you say, you know, on an average sense, yeah, this may be happening. But what if, is it possible that my parameters are not average? You know, yes, it's possible. In that case, can I be protective? So that is what I mean. So they're always looking at trying to do protective sort of modeling, just so down the line, you know, you're not sued by someone. Use well-established modeling and modeling methods. So again, open source, public domain, and communication. Then quantify impact of uncertainty is another big driver, because we've been 20 years ago, we were giving one model and decisions weren't very, people weren't very satisfied with the decisions with that. So that's where you need to look at multiple models, conceptual or parameter sensitivities, again, to the modeling objectives. Focus on your objectives. How does it matter to this objective, not to something else? And communication of that uncertainty. And finally, evaluate impacts of data collection, monitoring, and operational alternatives. So you can maximize impact of, you know, index wells. So you can place your centennial wells. Where do I need to monitor to be most effective? Minimize impact of uncertainty on the modeling objective. So again, this is data worth, same thing. Can I get the maximum out of my data? If I put a well here, is it worth it or not? So you can do that modeling a priori to let you know before you spend a lot of money throwing in a well, whether it's worth collecting data at that location or not. And then optimize impact of system operations and meet objectives. So that's the final reason why we are doing modeling, right? And the future of modeling, this is my last slide. Where are we headed? Well, I say we are headed in the right direction. Why? Because everything is increasing. Modeling, analysis, and needs are increasing. As our resources are getting more and more tight and depleted, we are trying to manage that little bit of water as well, you know. We are having technological advancements. So sensor technologies are increasing. So that gives us better information for the models. Tracer techniques. So when you're looking at contaminant migration, those are interesting, difficult, challenging problems. So they are helping with that. Geophysical methods are helping give more continuous data. I know Nebraska has the AEMs. They've been flying these aerial electromagnetic surveys, gives them that continuous data. I think it's very valuable for models. We need to have more continuous data in our models, including precipitation. So not, and I said this before, you know, not just rain gauges, but incorporate that with NextRad data from satellites, things like that. And it's coming. We have those things, they're happening. Physics, mathematics, and statistics are actually, there are lots of advances in that. Governing processes and equations, coupling of equations of processes, upscaling and downscaling processes are being understood better, you know. Numerical methods are improving, parameterization methods are improving, uncertainty evaluation methods are improving. Then modeling and related software is improving by leaps and bounds. We have the mod flows, we have the graphic user interfaces, we have tools which help you do the inverse modeling to calibrate your model, so you don't have to figure out what parameterization will help you resolve your observations. Particle tracking, so you can see traces of water, how things are moving. And you have 3D visualization capabilities. Hardware is increasing. So I think we are moving in the right direction. We are going to make better models. We are going to answer finer and finer resolution of questions. And that is my view of where we are headed. And I guess I can take questions. I took 40 minutes, right? And that's what I was told, Jesse. I could go on.
Thank you. Thanks, Sorab. No, I think we're in a good place with our timing. It's about 4:11 on my computer screen. Thanks for providing that overview of groundwater modeling. I made a comment in the chat box for people to use that as our vehicle to propose questions to Sorab. We have 46 participants on the call. It looks like a really a good group that is Nebraska heavy and has university and agency folks. So if there are questions, please enter them into the chat box and I will try to pick those up as they come along. Sorab, I'm just going to ask you a non-technical question, but I think it might help some of the people on the call. You, of course, you work in DC, but you're making time throughout the weeks and maybe during specific times where you are available to consult and work with different folks in Nebraska. Are there kind of set days and times and weeks that you do that, or what's the best way for people who may have questions to reach you?
You know, like I said, I give support on the codes that I've been developing to everyone. So it doesn't matter when you reach me if you need, modeling code support. My appointment is 1 week every 2 months, and that's flexible. And now instead of I'm zooming into Lincoln instead of physically being there. So this is kind of my week in Lincoln. I've been talking with people, but not too much. It's been more of a relaxed week here. So yeah, so people can access me. It's not a problem to access me.
Perfect.
I will have, yeah, and I've been helping some of the students also with their modeling. I haven't been helping truthfully. They've been running their models by me, and hopefully I may be helpful down the line when they have issues.
Okay, thanks, Sorab. In the meantime, 2 questions came in, so I'll take the first one here. The participant asks, what kind of modeling tool do you recommend to simulate surface water groundwater interaction?
Okay, again, it depends on, well, surface water groundwater interactions. The ModFlow set of tools can model surface water groundwater interaction in the sense of your groundwater to the stream. So when people talk about surface water interactions, they are mainly talking about interactions with streams. So the ModFlow suite of codes have modules which solve for that surface water flow. If you are thinking of how does rainfall go through the unsaturated zone, and in that sense, surface water groundwater interaction, typically what people have done is there are surface water codes like HSPF. That's a very common code which is being used for surface water. What it does is it uses what's called the curve number approach. It separates your precipitation or applied water into runoff and infiltration. And then from the infiltration, it looks at what your unsaturated zone evapotranspiration may be and sends the remaining water as recharge to your groundwater model. So people have, when those are your needs, objectives, then what people have done is linked a HSPF type model to a groundwater flow model. There are other things you could do, again, depending on your objectives. ModFlow also has unsaturated zone flow itself, so you could even do that. There is a GS flow model, which actually does the surface water routing, which is actually ModFlow with one of the USGS surface water flow codes called Prism. And that has been used also extensively for surface water groundwater interactions when you are looking at how precipitation is taken down to as recharge to the groundwater. But otherwise, if you're just looking at how stream interaction with groundwater, then ModFlow can take care of that. Okay.
Thanks, Sorab. The next question is, can you recommend any inverse models for stream flow for watersheds, 5,000 square kilometers, that have only one gauge at the outlet, can we apply inverse modeling to have stream flow estimates at sub-watersheds with acceptable levels of accuracy?
That's a very interesting question. People have tried to simulate what are called ungauged watersheds. In my past consulting life, I was doing this surface water, subsurface interactions, quite a bit of that. And what you have is, there are various ways where you can take the, there are various ways you can do that. There are different models that you can use. Can you tell me again what was the question there more specifically, Jesse?
Sure. Yeah, there was. He wrote. Could you recommend any inverse
Models? Yeah.
Mm-hmm.
So right. What people do there is, you see, you have a rainfall record, a precipitation record, and hopefully that is accurate. Okay, so everything depends on your information. So if you have NextRad information and you have some rain gauge information and you can try and marry the two, then that is good input. Then people are using more what are called physics-based spatially distributed models for that. So what you have is your surface water is not a lump model, but you put in your topography and you get that into the whole domain. You have put in a groundwater model also, so you get the base flow coming back out. So you have your recession curve on your stream flow hydrograph. And then if you can match the stream flow hydrograph at the bottom end, you use something like PEST, okay? Again, the information you've put in, like rainfall, is as accurate as you can get. The information for your DEM, your digital elevations, is as accurate as you can get. So your flow paths and all are as accurate as you can get. And then what are the unknowns? Things like how much is infiltrating versus how much is running off. And second thing is, well, how slowly or quickly the infiltrating water from groundwater is again coming back out to the streams. So that is what you're calibrating. So the recession part of your curve of your stream flow curve, say just if you are looking at just say a curve of a big rainfall event and how that recedes. And then for the peak flow, you look at the surface water runoff, like your Manning's N or something. So you can even do something like that manually. You can throw that in PEST. So PEST is a parameter estimation code. So if you do that, then you can have higher confidence that at your sub watersheds, which are ungauged, you are getting the right amount of flow. That's the best you can do, right?
Thanks, Sorab. We have another question here. What do you think big data and machine learning can help groundwater modeling? And will machine learning replace numerical models in the future?
Aha. So I am a big proponent of using machine learning. I can go for another lecture on that entirely. Machine learning, okay, so we have, what I see is we have big data, but we have small big data. We have big data, maybe we may have one well record from 1920 every half hour till now. That's a lot of information, but it's one well. So that's what I mean. It's small data. It's not, we don't have that distribution of data. So data sciences actually helps us a lot more because of that, not less, So I feel like how we are calibrating these, I could go on, how we are calibrating these models here, to some hydrologic information like water level fluctuations. There, we have some water level fluctuations here, and let me calibrate to that. Wonderful, I think with data sciences, there are so many things you can do. You can try and figure out what stresses are causing this signal. Is it rainfall? Is it pumping? So you can now separate your signals out. You can try and figure out which of these hydrographs are behaving in a similar manner. So you can do clustering. So then you can say, there's a lot of data uncertainty. So you can say, this one here, it says in the Evangeline, but guess what? The signature looks more like it's in the other aquifer, in the Jasper. So now you can assimilate your data much better. Now when you're calibrating your model, so I don't think it's going to replace models, because models can be used for looking at different things which is not there in your data. I can say, what if it didn't rain for 100 years? I can do that in a model. I can't do that with data itself, you see. So I don't think it'll replace models. Models are always going to be there, but I think there is going to be a huge place for machine learning, data sciences in modeling. And there are so many different applications. There's clustering, things like that, things like these TFN, transfer function noise analyses, where you are separating the different signals from the noise and from each other. So this is causing this signal and that is causing that signal. So now when you calibrate models, instead of calibrating it to just something complex, you can just say, let me just put this stress here and see if I can calibrate the model. Let me put that stress over there and see if I can calibrate that, broken up signal. And then you can put it all back together and say, hey, I can verify it that yes, I match everything. So you understand your models better. You are doing a better job of calibration. I could go on data sciences. I think I'd worked with some in the 90s, and you could do a little bit. Today, I think you can do a lot more. And in the future, we'll do a lot more with data sciences. Yeah.
So
Yeah,
Rob,
I'm very excited about it. So yeah.
We'll have to invite you back for the 2021 water seminar series.
All right, sure. Hey, my pleasure.
Another question that came in was about errors, and the participant wrote, how are errors in groundwater level measurement and stream flow measurements identified during calibration?
This is again comes back to data processing. During calibration, it might be hard to distinguish if it's an error or not, but definitely there's a saying, yeah, and this is a saying of, like I said, one of the students at UC Davis had this on his website, where it says, nobody trusts the model except he who wrote it, and everybody trusts the data except he who took it, and this is a problem. Data has errors in it, so you don't have to match that data exactly. If there are large errors in data, you see, data processing upfront will tell you that yes, in these sort of models, you have to do a lot of data processing. Is that water level in the aquifer? Is it something wrong? Is things like what I mentioned, the signature seems to be of one aquifer, but in your database, it looks like it's another aquifer, So there are lots of things like this.
Thanks, Sorab. If anybody has any other questions, it's 4:25. We have time. We usually go up until roughly 4:30. So feel free to enter those into the chat box.
I have this Chittaranjan, or maybe I'll just write it out. Sorry.
Sure. Thanks, Chittaranjan.
So the interesting thing, Jesse, is that I don't see the chat box.
Oh, I thought you would be able to as a co-host.
Right, but oh, there. 1 second, I see it now. Ah, yes, that helps.
while Chittaranjan is formulating his question, I sent a note out that the seminar will be available on the YouTube channel for the Water Center, and there's a link in the chat box too for people who want to follow that way. Okay, Chittaranjan's question is, Nebraska uses models for water policy. I think he's writing a, what about other states who do the same?
Sorry, can you say that again?
Yeah, Nebraska uses models for formulating water policy. Do you know of other states who do the same?
The same. You know, adjudication has, models have definitely been a part of adjudication in California. They look at safe yield and they calculate safe yield using the model. These are all prescribed in a courtroom. Let's put it that way. So I mean, policy, I don't know exactly if that's called policy, but there are judgments which say this is how you will be operating the basin, and everything depends on the models. The models get updated. So it's all in writings, even how, if there are errors, you know, how you will fix those. So when you update the model and it says, oh, my safe yield is 5,000 acre-feet less than it was from the previous model. So everyone comes together and says, you know, from their share, they remove that 5,000 acre-feet of stored water. So models have been used in that sense to, I don't know if you call it policy, but yeah, it's a prescription of the way to manage basins. Yeah. There is another question here I see is, would you prefer coupled model like SWAT mod flow over Mike Shee for groundwater, surface water, or something else? I see that. And again, it depends on the objectives, you know. It depends on what you're solving. That's all I can say. It depends on how fast things run. It depends on, you know, yeah, I have no, I mean, finally, which model you use depends on your objectives.
Okay.
Okay.
I think that's a good place to stop as we're just about at 4:30. Again, this is all soon to be archived material, and maybe now's a good opportunity just to thank you, Sorab, for taking some time to present your work. You've been working at this for a very long time and have developed a lot of expertise. So it was great to have it, you know, boiled down into a 45-minute talk. I also wanted to just thank all of the presenters and students who registered for the course that accompanies the water seminar, and then all the attendees who have come from what seems like a very long time ago now, on January 22nd, when John Niebuhr kicked us off.
Yeah.
But it's kind of full circle, because he was talking about Vados zone processes and modeling, and now we're back here underground again, and with some diversions for citizen science and water quality and surface water monitoring. So it's been a good series, and again, thanks to you, Sorab, and please do check the YouTube channel in the next, by Friday, I'd say, for the video to be posted on our channel. So with that, I think I will officially conclude the water seminar series, and we'll see you all for the next season.
Yes, thank you, Jesse. It was my pleasure to do this here. Have a great day, everyone. Bye-bye.
Thank
Thanks,
you very
Sorab.
much.